Good afternoon, everyone. My name is Dhiren Kesani, and I'm the team lead and software developer for our team, the Positioning Professionals. We have had the honor of being sponsored by TI for our 3D optical positioning system project. And Mikhail Tishitskin is our document manager and our microcontroller developer as well. And John Thurman is our software and GUI engineer. Nathan Smith is our hardware engineer, and Abdullah Khan is also our hardware and math engineer. And now I'm going to hand it off to Mikhail to talk about the project.
So modern day has put an increased emphasis on where objects are in 3D space. Things like the Kinect, things like VR, things like assisted driving, they all require you to know where objects are. And with those systems, they're integrated and they're high cost. And they're specifically designed to do their one thing. This gap is where we seek to fit in. Our system seeks to be low power, low cost, and generalized. So we want to focus on precisely figuring out where something is and giving that data to a user to then integrate into a larger system. So we decided to go with a photodiode-based sensor system. So we have our sensor block, we have an LED driver block with infrared LEDs, we have software that takes the sensor data and does math to figure out the position, and we have a microcontroller in the middle doing all of the handshaking. So our first major concern was with low cost and low complexity, and we mitigated that by using an 8x1020, which is an integrated photo sensor. It's got the photo integrator, it has an integrated analog to digital converter, and it has an integrated LED driver. This significantly brought down overall complexity of the system while slightly increasing programming complexity. And the increase in programming complexity we felt was more than worth the lower hardware profile of the whole system. So we have a TI MSP432 microcontroller which acts as basically a highway for all of the components. It calibrates the sensor initially, it facilitates data movement from the sensors to our software, and it also, using signals from the sensor, allows the LEDs to be driven such that the sensor can read and calculate the position of our object in 3D space. So our software then takes the raw data that our sensor gathers and proceeds to figure out, using optical angular measurements, where that object is in 3D space. It then can pass this information on to a larger subsystem, which we are not concerned with, but by providing this information, you can quickly integrate it to a variety of applications such as such as video games like flight controllers, or to things like 3D mice for 3D drawing. So at present, we are basically on the cusp of having a prototype ready, and for now we're focusing on our precision. So we've gone for a lower range design, but an enhanced precision of being able to track at least a meter per second motion above it with a 1 millimeter stationary accuracy. And we plan to get our working prototype very early first semester so that we can improve the performance metrics, we can improve the UI interface, and we can fine-tune the design in terms of power, in terms of signal noise, and we potentially have a stretch goal of doing a wireless mouse for second semester. And at this point, I'd like to open for any questions.
Is your sort of mental target the mouse? Is that the thing that you think this would be used for? Or
the simplest application would be a mouse, yeah. But our goal is to create a system that, instead of being like a Kinect sensor, which, yes, it does track position, but unless you basically rewrite the driver software of it, or you have a giant company like Microsoft implement an API specifically for that purpose, it's only designed to be used with the Xbox. And if you have like a Nintendo Wiimote, it tracks position only for the Wii. You don't have something that just feeds you raw positional data, which then you can use in a larger system like a 3D mouse or like a controller for a flight simulation.
So the objective is at least to be operable in a fixed climate type?
That's the initial yes. And based on the intensity we get from our sensor, we can have dynamic calibration for the LEDs so that we can either increase or decrease the range based on about where the object is.
And that's one of the key things. It doesn't have to be operating like in a black box or something and you stick your hand in and you move it like this. It's like, okay, I can have ambient light or any other factors like that and still be able to get really high precision.
Because we're only going off angle measurements in X and Y direction, not light intensity. So we get better results. We don't have to depend on, like, if it's a cloudy day, we're stuck. No, we have like we have more parameters than just like perfect
Light
sunlight.
intensity.
Yeah.
You open up your applications.
How does it know what to track if I put my whole hand over it? How does it know to track my hand versus my finger versus not? There's something else that's moving behind my hand.
There is an array of infrared LEDs that will attach to whatever object you want to track.
So like this image right here, it's tracking something,
Yes.
right? Is it just a finger? So that's the only thing moving and it doesn't see, so it can distinguish between.
So the software is tracking a specific object that is hooked up with the array of LEDs.
Okay.
So it's going to track a specific object that's meant to be tracked. It won't track any outside items. It's just going to track that specific
And
object.
it only tracks those LEDs because it's pulsed at specific times and it knows when it should be looking for the IR light.
Gotcha.
So this movable object is tethered.
Currently,
yes.
yes. That's why we have our second semester stretch goal of the wireless
It's
mouse.
tethered in the sense that it will always have to have some object with LEDs on it and like a mouse pad or something like that to receive the light. Yeah.
All right, let's thank